What if a skyscraper was already built before it left the factory? Not partially built, not framed out, not roughed in, built, finished, wired, plumbed, glazed, ready, and then someone drove it to a city and stacked it into the sky in 19 days. Welcome back to the channel. What you are about to watch is one of the most audacious, most disruptive, and most quietly revolutionary feats of construction engineering ever attempted by human hands. It is called Mini Sky City. It is 57 stories tall, and the construction industry has never fully recovered from watching it go up. This is not just a fast building. That framing is too small, too comfortable, too easy to dismiss. This is a complete reimagination of what construction even is. A philosophical challenge disguised as a steel frame. A statement that says everything you think you know about how cities are built is wrong, has always been wrong, and could have been done differently all along. Imagine standing on a factory floor in Changsha, China. In 2014, around you, the noise is overwhelming. Steel is being cut. Bolts are being driven. Electrical conduits are being threaded through pre-drilled channels in the floor panels. Plumbing runs are being pressure tested. Window units are being seated into frames and sealed. Workers with clipboards walk between rows of identical steel boxes, each one a room, a corridor, a stairwell section, a bathroom being completed under a roof. In controlled conditions, while outside, on a plot of land a few kilometers away, a foundation waits. This is not a construction site, this is a factory. But what it is making is a skyscraper. Every decision mattered, every millimeter mattered, every bolt hole mattered, because those boxes would travel from this factory floor to a city street, rise 57 floors into the Hunan sky. And then, with near surgical precision, locked together into one of the tallest buildings in the region, and they would do it in 19 days. Let us go back to the beginning. To understand what Broad Group achieved, you first need to understand what they were working against, not just engineering challenges, not just physics, but an entire civilization's worth of assumptions about how buildings get built. For roughly 5,000 years, the logic of construction has been the same. You go to a site, you dig, you pour, you frame, you cover, you wire, you plumb, you finish. One phase ends before the next begins. Concrete has to cure, and curing takes time that nothing can speed up. Not money, not manpower, not ambition. A 50-story building constructed this way takes 2 to 3 years at minimum. 3 years of weather delays. 3 years of coordinating hundreds of subcontractors. 3 years of scaffolding, noise, dust, and danger for the workers and the neighborhoods around the site. This is not because engineers are slow, it is because this is what physics and chemistry demand. You want reinforced concrete? It will cure in its own time. You want structural steel welded in place? Each weld needs inspection, cooling, re-inspection. You want complex MEP systems, mechanical, electrical, plumbing, to be threaded through a finished structure. Prepare to send workers into tight, awkward, already complete spaces with hand tools and patience and prayer. This is the normal world. This is how every city on Earth has been built since cities began. And then a man named Zhang Yu decided the normal world was not good enough. He built his company Broad Group on air conditioning, specifically on non-electric absorption chillers that could cool enormous buildings without using grid power. He was already an unconventional thinker. He had already decided before he turned to buildings that the standard way of doing things was simply a failure of imagination. So when he turned his attention to construction itself, to the fundamental process of how buildings go up, he brought with him the same mindset, the same refusal to accept that just how it's done as an answer. The question he asked was devastatingly simple. Why are we building at the site? Think about that question. Really sit with it. In almost every other manufacturing industry, we long ago decided that quality control happens in factories. Cars are not built on driveways. Airplanes are not manufactured in the offices. Marred breezes, where they will eventually be used. We bring raw materials into a controlled environment. We apply precision processes under consistent conditions. But buildings are still manufactured on site, in the rain, in the cold, in the heat, with changing crews, changing conditions, changing tolerances, with materials delivered at inconsistent times, with concrete mixed and poured in weather that affects its chemistry, with inspections happening not in a quiet factory bay, but on a windswept scaffold, 40 floors above a city street. Zhang Yu looked at this and saw not tradition, but waste. Inefficiency, a system that had calcified around its own constraints without ever questioning whether the constraints were necessary. And so he built a different system. He called it Broad Satellite Building Technology, BSB. And the core idea is almost insultingly Eders. Build the building in a factory, in modules complete from floor to ceiling, and then bolt the modules together on site. Not weld, bolt. This distinction matters more than almost anything else in this story. When structural steel is welded, the weld must be inspected, must cool, must sometimes be X-rayed for internal defects invisible to the naked eye. This takes time. A single weld on a critical joint can delay an entire floor, progress by hours. But when steel modules are bolted, when the connection is mechanical, visible, immediate, and inspectable in seconds, the pace of assembly becomes almost incomprehensible. A bolt goes in. It is torqued to specification. An inspector checks the torque value. Done. Next bolt, next module, next floor. This was not simple. This was a revolution in disguise, wrapped in ordinary fasteners that anyone could understand, hiding a transformation that would challenge the construction industry to its core. But before any module could be bolted, before any floor could rise, before any worker could stack steel boxes into a tower, something else had to happen. Something that took not days, but months. Something invisible to the cameras that would later broadcast the 19-day assembly to a stunned world. The factory phase. Let us be precise about something that the viral videos almost always get wrong, or rather, what they leave out. When people say Mini Sky City was built in 19 days, what they mean is that the on-site assembly, the stacking, the bolting, the connecting of modules that were already complete took 19 days. What they do not mean is that the entire building went from nothing to finished in 19 days. That would violate physics, and physics cannot be negotiated with. What happened before those 19 days is arguably the more extraordinary story, because in a factory in Changsha, for several months before a single module arrived at the site, broad group, engineers and workers were building the sky. They were manufacturing floor panels, steel-framed composite panels, pre-drilled, pre-measured, designed to interlock with sub-millimeter tolerance. They were fabricating column sections, beam sections, stairwell cores, elevator shafts, all in pieces sized to be transported on standard flatbed trucks, to fit under bridge overpasses, to pass through city streets without special permits or road closures. They were installing inside each module while it sat on a factory floor, at a comfortable working height, the complete infrastructure of modern habitat, the electrical conduits and junction boxes, the plumbing supply lines and drain stacks, the HVAC ductwork, the insulation layers, the quad-pane window units, the flooring surfaces, the ceiling finishes. Every wire was run. Every pipe was pressure tested. Every window was seated and sealed. Before the module left the factory floor, it was inspected. Before it was loaded onto a truck, it was re-inspected. By the time it reached the site, the only work remaining was lift it into position, align it to the module below, drive in the bolts, connect the service penetrations between floors, and move to the next one. This is the revolution. This is the thing that breaks people's brains when they truly understand it. The complexity of a skyscraper, the breathtaking coordination of systems that normally has to happen inside a finished structure in cramped and dangerous conditions by work until it is too late to change it, had been moved, relocated, exported from the site to the factory, from chaos to control, from weather to shelter, from unpredictability to precision. And this transformation had a second-order effect that Zhang Yu's team had not fully anticipated when they began, but which became one of the most powerful arguments for the entire SIS, because the factory produced identical standardized modules. The quality of every room in the building was essentially identical. The first floor and the 57th floor were assembled by the same jigs with the same tools, to the same tolerances. There was no bad floor where the concrete crew had rushed, where the plumber had cut a corner, where the inspector had passed something borderline on a Friday afternoon. Every module mattered. Every inspection mattered. Every tolerance mattered. Now let us go to the site itself. The ground in Changsha had been prepared. A conventional reinforced concrete foundation, because the ground always needs this, regardless of what goes above it, had been poured and had cured. This part of the process followed standard practice, because there is no clever trick that makes concrete cure faster. The foundation is the one part of a BSB project that looks like ordinary construction, and it has to be perfect because 57 floors of steel modules will rest on it forever. The foundation is not just a flat slab. It is a precisely engineered grid of connection points, anchor bolts, leveling plates, conduit penetrations, each positioned to receive the first layer of modules with the same interlocking precision that all the layers above will rely on. If the foundation is off by even a few millimeters in the wrong place, the error does not stay at ground level. It propagates upward. It compounds. By floor, 20 a millimeter at the base could mean centimeters of misalignment at the top. So the foundation was surveyed, then surveyed again, then checked against the factory drawings with laser measurement tools, then signed off by multiple engineers before the first truck convoy was allowed to approach. And then the trucks arrived, flatbed after flatbed after flatbed, rolling through Changsha streets in the early hours of the morning to avoid traffic, each truck carrying modules, numbered, pre-sequenced, pre-cataloged in a delivery schedule that works like a three-dimensional jigsaw puzzle because the modules could not simply arrive in any order. They had to arrive in the order they would be installed, because the site had no warehouse, no staging yard large enough to store everything at once. The building supply chain was as precisely choreographed as its assembly. This was not simple logistics. This was a dance. The modules arrive, the crane, a single tower crane, positioned at the building's center, lifts each module from the truck. The rigging crew attaches the lifting points. The signal is given. The module rises above it. Workers on the previous floor guide it in with hand signals and radio calls, coaxing it millimeter by millimeter into its final position. The alignment pins engage. The module settles. Bolts are driven, dozens of them, connecting the new module to its neighbors on all sides. Workers check torque values. An inspector marks each bolt with a paint pen indicating its torque status. A supervisor signs the floor card, and the crane goes back down. Another module, another floor, hour after hour, through the day, into the night, under floodlights, in shifts, without stopping. Because this is the other thing that the factory model enables: continuous operation. On a conventional construction site, night work is often impossible or severely restricted. The concrete pour cannot happen safely in darkness. The iron worker cannot weld safely on a rain-slicked scaffold at midnight, but the assembly of pre-built modules, that can happen around the clock. The work is bolting. The work is connecting. The work is mechanical and inspectable, and safe regardless of whether the sun is up. So the teams worked in shifts, and the building rose, not slowly, not over months of grinding incremental progress, but visibly, hour by hour, in a way that ordinary people walking past the site could see with their own eyes. A floor that did not exist at breakfast existed at dinner. Workers who had never seen a building go up this fast stopped and watched. Residents in neighboring buildings filmed with their phones. Engineers who flew in from other cities stood on the pavement and shook their heads. This was not normal. This was not supposed to be possible. And yet the physics of it, once you understand the system, is entirely coherent. Because the heavy work, the complex, time-consuming, skilled work of actually making a building habitable had already been done. What was happening on site was assembly, not construction, installation, not fabrication. Placement, not creation. The sky was being claimed. floor by floor, bolt by bolt, in a pace that had no precedent in the history of tall building construction. But the story of Mini Sky City is not only a story about speed. Speed is the headline. Yes, speed is what made the world pay attention. But the deeper story, the one that kept structural engineers up at night, is about what the building could withstand. A skyscraper has to do more than stand. It has to survive in a seismically active country. And China, particularly its southern and central provinces, experiences significant seismic activity. The question of earthquake resistance is not academic. It is existential. And when Broad Group announced that their BSB system was designed to withstand a magnitude 9.0 earthquake, the engineering world leaned forward in their chairs. 9.0 on the Richter scale is not a tremor. It is a planetary event. The 2011 Tohoku earthquake that devastated Japan was magnitude 9.0. The 1960 Valdivia earthquake in Chile, the most powerful ever recorded in human history, was 9.5. When Broad Group said their building was designed for a 9.0, they were saying something extraordinary. And the reason they could say it traces back directly to the factory system. Steel is, as a structural material, inherently more earthquake-resistant than concrete. It bends without breaking. It absorbs energy through deformation rather than brittle fracture. Concrete, without extraordinary reinforcement, will shatter under seismic loading. Steel flexes, and a building made entirely of interlocking steel modules, each one a rigid box, connected to its neighbors by bolted joints that can absorb shear forces across their full surface area, behaves under seismic loading in a fundamentally different way than a concrete frame. The modules do not just sit on each other, they interlock. The bolted connections create a three-dimensional grid of structural continuity, what engineers call redundancy. If one joint experiences extreme stress, the surrounding joints share the load. The building does not have a single critical point of failure. It has thousands of connection points, each contributing to the whole, each participating in the resistance. This was not simple. This was structural engineering of a very high order, dressed up in the visual language of simplicity because the individual pieces looked so unpretentious. A steel box, a bolt, a floor panel, a bolt. It looks almost humble. But the system, the engineered interaction between all those humble pieces, is anything but. And then there was the insulation. Here is a detail that does not make the viral videos. Here is the part that got buried under the headline, but it may be one of the most important things about BSB construction from the perspective of the 21st century. Each module built in the factory was insulated to a standard that conventional construction almost never achieves. Not because it is impossible to achieve in conventional construction, but because it is extraordinarily difficult and expensive to do so on a site with workers threading insulation bats between already framed studs in cold and cramped conditions, where gaps and compressions and thermal bridges are nearly inevitable. But in a factory, on a bench, with a template, with a quality inspector standing 3 meters away, the insulation goes in perfectly. The vapor barriers seal completely. The thermal bridges, those points where heat can leak from inside to outside through a conductive material, are engineered out of the module design itself. Broad Group claimed their buildings used roughly 5 times less energy than comparable conventional buildings. The quad-pane windows, 4 layers of glass, with 3 insulating air gaps, rejected heat in summer and retained it in winter, at a level that most buildings in the world do not approach. The thick wall assemblies, with their factory, perfect insulation. This was not just engineering efficiency. This was a quiet argument about climate, about energy, about what cities of the future would need to look like if the planet was going to survive its own population. And it was all made possible, only made possible by the factory model. Because in the factory, perfection is achievable. On the site, perfection is merely aspirational. Every window mattered. Every insulation layer mattered. Every vapor barrier mattered. And they got them right. Every time, in every module, in every floor, because the system demanded it and the factory enabled it. By the time day 10 of the 19-day assembly arrived, The building was already a presence on the Changsha skyline. Workers on the upper floors could see for kilometers in every direction. The city spread out below them, its river, its bridges, its older buildings rising by conventional means, slowly, over their years of scheduled progress. And here 57 floors of steel and glass and precision were being stacked into the sky. Floor by floor, faster than any building in the history of human civilization. The crane did not stop. The trucks did not stop. The shifts did not stop. Day 10 became day 12. Day 12 became day 15. The upper floors were being installed while workers on the lower floors were connecting the service penetrations, the electrical junction points between modules, the plumbing couplings, the data conduits that would tie the entire building's systems together into one functioning whole. This is the part that is hardest to visualize, because each module arrived pre-wired and pre-plumbed internally. But at the boundary between modules, at the interface where one box meets the next, there are connection points, carefully designed, precisely located, standardized connection points where one module's electrical system handshakes with its neighbor S, where one module water supply meets the riser that feeds the floor above. These connections had to be made. They were not automatic. They required workers. But they required far fewer workers than conventional building MEP installation, because the connections were standardized, accessible and located in positions that the factory had pre-cleared for easy access. There were no walls to cut into, no ceilings to remove, no chase walls to open. The connection point was there. The tool fit it. The worker made the connection. The inspector verified it. Move on floor by floor, system by system, floor by floor, until day 19 arrived and the last module rose on the crane hook and the rigging crew guided it into position on the 57th floor and the alignment pins engaged, and the bolts were driven and the torque wrench was applied, and the paint pen marked each bolt head, and Mini Sky City was standing 57 stories, approximately 200 meters of steel and glass and precision and audacity and one man, refusal to accept that a building had to take 3 years to build. 19 days. The world watched the time-lapse footage and did not believe it. Engineers watched it and demanded explanations. Journalists watched it and reached for superlatives. Ordinary people watched it and felt, mixed with the wonder, a small needle of unease. If this was possible, if it had always been possible, then what did it mean that no one had done it before? What did it mean that entire city skylines around the world had been built with slower, noisier, more dangerous, more wasteful methods? When this was waiting to be invented, what did it mean for the workers whose livelihoods depended on conventional construction? What did it mean for the concrete industry, for the scaffold rental business, for the thousands of tradespeople who had built their careers on the fact that buildings took time, lots of time, and that time, measured in labor hours and site days, where their income lived? Mini Sky City was not just a building, it was a disruption. And disruptions in the construction industry, as in every other, do not arrive without consequence. But disruption is never clean. Disruption is always, in the end, a human story. And human stories do not resolve in 19 days. Let us talk about what happened after the last bolt was driven. After the last module was signed off, after the time-lapse footage went around the world and landed in the inboxes of architects, engineers, developers, and construction executives on 6 continents. Let us talk about what Mini Sky City revealed, not about China, not about steel, not about prefabrication, but about the industry it challenged, about the interests it threatened, about the questions it forced people to ask when they would have very much preferred not to ask them, because the building went up in 19 days. But the world's response to it has been going on ever since. Let us begin with what is inside the building that the viral videos never showed you. Most people who watched the assembly footage saw modules. They saw a crane. They saw steel boxes rising, one after another, into the Changsha sky. They saw a building appear where no building had been. And they were astonished by the speed. They did not see the interior of a module before it left the factory. They did not see the 4 layers of glass in every window, 4 panes, 3 air gaps, each gap filled with argon gas. a noble gas chosen precisely because it conducts heat far less efficiently than ordinary air. They did not see the seals around those windows, applied in the factory compressed during installation, forming a barrier between inside and outside that most conventional buildings. They did not see the insulation, the layers of mineral wool and rigid foam board installed flat, without compression, without the gaps and thermal bridges that inevitably appear when insulation is retrofitted into a framed wall on a windy construction site by workers who are cold and tired and have 40 more walls to go today. They did not see the floor panels beneath the finished flooring, composite steel panels with integrated channels for underfloor heating distribution, installed in the factory, pressure tested in the factory, sealed in the factory. They did not see the ceiling assemblies integrated with HVAC distribution, with lighting fixtures pre-positioned, with access panels located precisely where the service penetrations between modules would require them. They did not see the acoustic isolation between floors, the carefully engineered decoupling between the steel structure and the finished surfaces, designed to prevent the transmission of impact noise that plagues conventional steel. Frame buildings where a footstep on floor 37 is audible on floor 36. They did not see any of this, and they thought remarkable speed. What a fast building! But the engineers who looked more carefully, the ones who pulled up Broad Group's technical documentation and read it page by page, late into the night, understood something different. They understood that the speed was almost a side effect, that the real achievement was the months in the factory. The real achievement was what was inside, because buildings are not just structures. Buildings are systems, and systems assembled under controlled conditions by trained workers with precision tools and immediate inspection are fundamentally different from systems assembled in the open air under time pressure by rotating crews. The building that went up in 19 days was not a fast building. It was a better building. And that distinction, that crucial, uncomfortable distinction, is what kept structural engineers and building physicists up at night. Now let us address the earthquake. Not the metaphorical earthquake of disruption. The actual, geological, seismic loading kind. Broad Group's claim was specific. The BSB system was designed to resist a magnitude 9.0 seismic event. This is not a claim made lightly in structural engineering. A magnitude 9.0 is not a strong earthquake. It is a catastrophic one. It releases energy equivalent to thousands of nuclear weapons detonating simultaneously in the Earth's crust. It moves the ground, not in centimeters but in meters. It liquefies soil, collapses bridges, triggers tsunamis, reshapes coastlines. For a building to survive such an event, it cannot simply be strong. Strength alone is not enough. A building that is too rigid, too brittle, too resistant to deformation will shatter under seismic loading even if its materials are individually extremely strong. Concrete is the perfect example. Concrete is very strong in compression. It can bear enormous vertical loads, but under the lateral forces of an earthquake, which push a building sideways, back and forth, at frequencies that interact with the building, natural resonant frequency. Concrete fails suddenly, catastrophically, without warning. Steel does not fail that way. Steel yields, steel bends, steel absorbs energy through deformation rather than releasing it all at once through fracture. And a building made entirely of interlocking steel modules, connected not by welds, which can be brittle at their edges, but by bolts which allow the joint to flex slightly before transferring load, behaves under seismic loading in ways that structural engineers can model. But there is more to it than the material. The geometry matters. Each module in the BSB system is a closed steel box. A box, as any structural engineer will tell you, is one of the most inherently rigid geometric forms that exists. Unlike an open frame, 4 columns, and a few beams, a closed box resists deformation in all directions simultaneously. It is a 3-dimensional rigid body. Stack those rigid bodies together, bolt them to each other across their full face, and what you have is not a collection of boxes. You have a 3-dimensional grid of interlocking rigid cells, each one braced by all of its neighbors, the whole assembly behaving more like a single monolithic structure than like a collection of separate pieces. This is what engineers call a tube. Within tube system, or more precisely, a space frame with cellular redundancy. The loads do not travel through a single path from top to bottom. They distribute. They spread. They find the path of least resistance through a network of connections so numerous that no single failure can propagate catastrophically. Without this redundancy, a single failed column means a failed building. With it, a damaged module, a broken connection, a yielded joint means nothing worse than a local anomaly in a structure that continues to stand. This was not simple. This was structural engineering of a level that most conventional buildings, do not approach. And it was achieved not despite the factory method, but because of it. Because only in a factory can the tolerances required for this kind of interlocking precision actually be maintained. On a conventional site level precision over 57 floors is aspirational. On a factory floor, with laser measurement and jig-based assembly, it is achievable. And the difference between aspiration and achievement in structural engineering is the difference between a building that survives a magnitude 9.0 event and one that does not. And then there is the energy, the quiet revolution that nobody discussed at dinner parties. Broad Group published figures suggesting their buildings consumed roughly 5 times less energy. 5 times, if those figures are even approximately accurate. And they have been referenced in enough independent engineering analysis to warrant taking them seriously. The implications are staggering. Because energy consumption in buildings is not a minor issue. Buildings are responsible for a substantial portion of global energy use. Heating, cooling, lighting, ventilation, the systems that make an enclosed space habitable consume energy on a scale that rivals transportation, that rivals industry, that rivals agriculture. A world in which buildings consumed 1/5 of the energy they currently use would be a world with a fundamentally different relationship to climate change. The quad-pane windows were part of it, the factory. Perfect insulation was part of it. The thermal mass of the steel modules themselves, combined with the absence of thermal bridging, was part of it. But the energy efficiency of a BSB building was also a function of its tightness, the degree to which the internal envelope excluded uncontrolled infiltration of outside air. In a conventional building, air leaks through every crack, every gap, every imperfectly sealed penetration. These leaks are small individually. Collectively, they represent an enormous and continuous drain on the building's heating and cooling systems, which must constantly compensate for the uncontrolled exchange of conditioned inside air for unconditioned outside air in a factory-built module. Sealed at the factory, resealed at each connection on site, the airtightness is qualitatively different. Not zero, no building is completely airtight, nor should it be, since humans need fresh air, but controlled. The air that enters where it is designed to enter, through ventilation systems with heat exchangers that recover the energy from exhaust air before it leaves the building. This sounds technical. It sounds abstract, but the practical consequence is simple. The building keeps its warmth in winter and its coolness in summer not through the continuous effort of its mechanical systems, but through the passive excellence of its envelope. The building itself does the work. Before any system switches on, every window mattered. Every seal mattered. Every millimeter of insulation mattered. And they all mattered because in a factory they could all be done right. Every time without exception. Now let us talk about the world's reaction. Because the world's reaction is, in its way, as instructive as the building itself. The time-lapse footage of Mini Sky City's assembly was released in 2015 and spread across the internet with the velocity that only truly astonishing things achieve. It was shared by engineers, by architects, by urban planners, by journalists, by ordinary people who had no professional interest in construction, but who understood. The reactions sorted themselves into categories that were almost entirely predictable once you understood the interests at stake. The first category was wonder, pure unqualified wonder. This came mostly from people with no professional connection to the construction industry, people who could simply appreciate what they were seeing without calculating what it meant for their livelihood. This came from engineers, some of them genuinely curious, some of them instinctively protective of the norms they had spent careers. Mastering the questions were reasonable. What are the long-term settlement characteristics? How do the bolted connections perform under repeated thermal cycling? As the building expands and contracts with seasonal temperature changes, what happens to the airtight seals over decades of use? How is maintenance and replacement of individual modules handled when one is surrounded on all sides by its neighbors? These are not hostile questions. These are real engineering questions. And Broad Group's answers to them were, in some cases, more complete than the skeptics expected, and in other cases, genuinely unresolved, because the BSB system, for all its revolutionary qualities, was still a young technology. The third category was institutional resistance. This was quieter than the other two, less visible in public forums, but more consequential in its effects. Because the construction industry, not the individual engineers and architects, but the institutional structures around them, the standards bodies, the insurance underwriters, the building code committees, the professional licensing boards, these institutions move slowly. They are built to move slowly. They are built to protect against exactly the kind of rapid, unvalidated change that Mini Sky City represented. And this institutional resistance is not entirely wrong. Building codes exist because buildings fell down. Fire codes exist because buildings burned. Structural standards exist because structures collapsed. The caution embedded in these institutions is paid for in historical disaster, and discarding it too quickly is genuinely dangerous. But the institutions also have another function, one less noble, one that they rarely announce. They protect established practitioners. They create barriers to entry. They define what counts as proper construction in ways that tend to favor methods and materials. And when a technology arrives that sidesteps those barriers, that produces results that are equal or superior by every measurable standard, through methods that existing practitioners do not control, the institutions do not always respond with open arms. Mini Sky City arrived in a world of building codes that were written for conventional construction. Codes that specified minimum curing times for concrete times that become irrelevant when there is no concrete to cure. Codes that required inspection protocols for welded joints, protocols that become unnecessary when the joints are bolted. Codes that assumed a site, built construction sequence, assumptions that simply do not apply to a building assembled from factory. To use BSB technology globally, Broad Group would have had to engage with building authorities in dozens of jurisdictions, in dozens of countries, each with their own codes, their own standards, their own approval processes. Each of those processes would require testing, documentation, third-party verification, pilot projects, and time. Years of time. Decades, perhaps. Zhang Yu had built a building that defied time on the construction site, and now time, institutional time, bureaucratic time, the slow grinding time of regulatory approval, was the obstacle he could not bolt together in 19 days. There is also the question of the workers. It is important. It needs to be said directly. The BSB system, if adopted at global scale, would fundamentally transform the labor economics of construction. Not eliminate construction work. The factory itself requires workers, skilled workers, workers trained in precision manufacturing rather than site-based trades. But the ratio of labor hours to floor area built would shift dramatically. And many of the specific skills that command premium wages in conventional construction, the concrete finisher, the site iron worker, the scaffold-based MEP tradesperson, would become less central. Zhang Yu was not unaware of this. In interviews, he addressed it directly, arguing that factory manufacturing creates safer jobs, better paid jobs, jobs in climate, controlled environments rather than on windswept scaffolding, 40 floors up. He is not wrong that factory work is, in most measurable ways, safer than site-based construction work. The construction industry has one of the highest rates of workplace injury and death of any major sector. Moving work from sites to factories would save lives. But the transition would not be smooth. Workers whose skills are site-based do not automatically become factory workers. Communities built around conventional construction trades do not simply absorb the disruption of a paradigm shift. And the construction industry, which employs tens of millions of people worldwide, which is the backbone of economic activity in many developing countries, which represents a vast accumulated base of human knowledge and craft, does not transform overnight, even when the technology that would transform it is clearly superior. This is not a reason to stop innovating, but it is a reason to be honest about what innovation costs. And who pays that cost? Every technology that has ever made human life better in the aggregate has also, in the short term, made specific human lives harder. The people who bore those costs were not abstractions. They had families, mortgages, trade certifications, earned over years of apprenticeship. They deserved to have their situation acknowledged, not dismissed. Mini Sky City was a building, but it was also a signal, and signals once sent cannot be unsent. So what happened next? What became of Zhang Yue's ambition to sell this technology to the world? The answer is honest and somewhat melancholy. Broad Group continued to develop the BSB technology. They built more projects. They refined the manufacturing process. They accumulated performance data on their completed buildings. Zhang Yue continued to advocate, continued to give interviews, continued to propose ever more ambitious projects, at one point announcing plans for a kilometer-tall building using BSB technology, a proposal that attracted enormous media attention. The kilometer-tall building was not built. The global revolution in construction did not happen on the timeline that the 2015 footage seemed to promise, but something subtler happened, in slower to unfold, but may ultimately be more significant. The ideas behind BSP technology, prefabrication, modular construction, factory-built assemblies, designed for manufacture and assembly, these ideas did not go back into the box that Mini Sky City opened. They spread. They infiltrated. They became part of the conversation in architecture schools and engineering firms and real estate development offices around the world, not under the Broad Group brand, not using BSB technology specifically, but in 100 variations, 100 adaptations, 100 attempts to capture some portion of the efficiency and quality that factory manufacturing offers with how an entire industry operates. Model housing in Scandinavia, prefabricated bathroom pods in high-rise construction in Singapore, factory-built timber frame panels in Austria and Switzerland, volumetric modular construction in the United Kingdom, cross-laminated timber assemblies in Canada and Australia. Each of these is a different material, a different scale, a different application, but all of them share a philosophical ancestry, the recognition that quality control happens in factories, not on sites, and that the future of construction lies in moving more of the process off the ground and under a roof. Mini Sky City did not build that future alone, but it showed it was possible. And possibility, once demonstrated, is very difficult to demonstrate. There is a question that Mini Sky City leaves unanswered. A question that sits at the center of this story like a structural column at the center of a building, bearing the load of everything above it. The question is this: if this technology was available in 2011, and if it is genuinely faster, genuinely safer, genuinely more energy efficient, and genuinely more structurally resilient than conventional construction, then why are the cities of the world not being built this way? Why are there still concrete mixers on city streets at 6 in the morning? Why are there still scaffold towers climbing the faces of buildings under construction in every major city on Earth? Why are workers still threading plumbing through already framed walls in conditions that no factory would permit? Why, 15 years after a 30-story building went up in 15 days, is a 30-story building still expected to take 3 years? Many reasons: inertia, institutional resistance, regulatory complexity, the difficulty of establishing new supply chains, the challenge of training a workforce in new skills, the financing structures of real estate development, which are built around conventional construction times and struggle to accommodate the upfront capital intensity of factory manufacturing, the conservatism of insurance underwriters who price risk based on historical data from established technologies, the preferences of end users who sometimes distrust buildings they know were prefabricated even when those buildings are demonstrably superior to the alternative. All of these are real. None of them are insurmountable. And none of them are good enough reasons to accept a world in which buildings take years to build in which construction workers die at rates that would be considered unacceptable in almost any other industry, in which the energy performance of the built environment continues to fall far short of what the climate requires. The question Mini Sky City asks is not really about buildings. It is about whether industries can change, whether entrenched systems can be disrupted by demonstrably better ideas, whether the gap between what is technically possible and what actually gets built is a gap that human beings with their institutions and their interests and their very reasonable fear of change are capable of closing. Zhang Yue drove across that gap in 19 days. The rest of the world is still standing on the other side, watching. 57 floors, approximately 200 meters of answered question, rising into the Changsha sky. 19 days of assembly, preceded by months of factory precision, preceded by years of a single man's refusal to accept that the normal way was the only way. The bolts are still torqued to specification. The quad-pane windows are still rejecting heat, retaining warmth, separating inside from outside with a precision that most buildings in the world did not achieve. The building stands. It has stood through heat and cold and wind and the vibrations of a city going about its ordinary, beautiful, oblivious life beneath it. And somewhere, in architecture schools, in engineering firms, in the offices of developers who are trying to figure out how to build more housing faster, with fewer resources and less waste. The idea that Mini Sky City planted is still growing. Every building tells a story. This one told the story of what construction could be. Whether the world is listening, whether it will listen in time, is a story that is still being written. If this video made you think differently about how cities are built and about how much faster, safer, and better they could be built, then this channel is exactly where you should be. Subscribe. There are more stories like this one waiting for you. More buildings that broke the rules. More engineers who refused the normal answer. More moments where human ingenuity looked at the impossible and said, "Not impossible, just not done yet." Thank you for watching.